Yes. So you tell me, Alex, if it is okay. So I was saying that thank you very much for the organizer. I also share my deepest sympathies to the family of Asen Donchev, of Asen, his wife, and his daughters. Unfortunately, I was not so close to him like you, some of you. But of course, as everyone of my generation, I have the chance to have on my hand lot of work, lot of research. Actually, I remember that when I started my thesis, the first question I had to deal with was about Lusternic theorem and its extension. And I had the chance to find a lot of work of some of you, of course, and also a lot of I had based a lot of work of Asen. It is okay, Alex? Do you hear me?
Yes, everything is perfect. Go ahead.
Thank you. So thank you very much again. This is my talk deals with convexity, with relation with convexity and projection. Actually, I will talk about is how is existence of projection, the size of projection is related to no convexity. The title of the talk is technical terms, but it is so simple. It is dual estimates of no convexity of sets in Hilbert spaces, a quantified version of Klis theorem. Actually, this is ongoing work with Aris Danilidis and Claudia Soto. Claudia Soto is from Universidad de Chile. So to measure no convexity, of course, convexity is very nice property in variational and no smooth analysis. But what can we do if we don't have this such nice property? There are ways to measure the no convexity. The natural one that we have at hand is the Hausdorff distance. Just to measure the Hausdorff distance from the convex hull of the set, the given set A to the set A, and as classically is defined, this is the small radius of the ball, yes, that contain the convex hull of A. There is another technical function called effective standard deviation function. This function is defined this way. Given a point X, so I look for all the possible combination of the point X that the appealing point Xi belong to A, and I do this estimate, and I take the infimum over all such X. This is called the standard deviation function. The word absolute is when instead of the norm square, I take the norm here. This is one function that actually we will use in this talk, in this work. There are many other ones. Actually, volume deficit, roughly speaking, is this compute the difference of the volumes between the convex hull and the set A. Another one is the Schneider no convexity index, and many others. Actually, this topic also concerns not only the community of variation optimization and variational analysis, but also community of geometry, which seems two different communities. Of course, if the Hausdorff distance is equal 0, yes, this equivalent to say that the set A is convex. I suppose that A is a subset of Rn and compact. And we can also check that, assuming that the supremum of this deviation function on the convex hull of A is 0 is equivalent to convexity. Actually, this is a way to check convexity of set. Yeah, but this is the difficult way. Actually, these functions are used even more to estimate how much do we lack convexity of the set. Yes. Let us see this simple example. My set is this one. yes, is not convex. And to have the convex hull, I completed with this part, the yellow part. The question we ask, what is the amount of the distance, Hausdorff distance between the set? So what we look for is to take all points in the convex hull and look for the projection. Actually, the only bad point where the projection is not unique is the point X of the half. All these, I mean, which are out in the boundary of the set. If you take any point in this part, has a unique projection. The only point X of the half has two projections, P by Px. There are two projections. And this is the highest amount of distance from the point X and its projection. Actually, this would be a possible estimate of the non-convexity of the set. Perhaps it is difficult to do this for all this point. So what we propose is to compare this distance with the diameter of the projection of the set of projection. Actually, is this one here. Yes, and as we see, this distance from X to the projection, which is the Hausdorff distance of the set from its convex hull, is always less than or smaller than the diameter of the projection. So this is why in the title I put dual. So instead of testing the amount of the amount of the distance from X to all the projection, a way to estimate this or to have an error or bound of this is to consider only all the projection of the points and consider the size of the projection. Yes, actually, what I do here, I consider all the point X, see what are the projection set. In all these points, the projection is singleton, so diameter is 0. The only point which has projection with no zero diameter is this point X here. And so I say that one upper bound of the Hausdorff distance between A and its convex hull is the diameter of this of the projection of the point X. So this is the idea. Replace this Hausdorff distance by means of the size of the given projection. Yes. This result may be useful in computation, but also it can be used for other theoretical results. Let us recall, for instance, this theorem called Shapley-Folkman-Starr theorem, which says the following: if you have in Rn, if you have any set A, and each time you consider the set AK, which is the sum, the k times sum of the set A divided by k. Yes, remember that the set A is not convex. So what the theorem said that larger is the parameter k, closer the set AK is to the convex hull, or said in another word, the AK converge in the Hausdorff distance to the convex hull of the set A. And actually, the result is even more precise. It gives us exactly the amount of the rate of the convergence is. N here is the dimension of the space. K is the number of iterates. So how can our dual representation of the distance Hausdorff can be used to explain this result? Actually, remember that the convex hull of the set A is the same as the convex hull of the set AK. Yes. So the distance Hausdorff of the convex A from the convex hull of the set A to AK, which is the same as the Hausdorff distance of the convex hull of AK to AK, what we pretend is that this is measured by this quantity, the diameter, the supremum over all x in the convex hull of the diameter of the projections. So here, this is what we pretend to prove in this talk or in this work. Control, or have to have a control about the Hausdorff distance. We see that this may be difficult to calculate by means only of the diameter of the projection. Yes, actually, this theorem, just I recall here, is useful in economic theory, in mathematical economics, for the existence of equilibria for problems having very large number of agents, and also in the problems of calculus of variation, where this theorem, Shapley-Folkman theorem, is equivalent to the so-called convexity or convex Lyapunov theorem. So let us see just that this property on a simple example, which is consider A to be just set of two different points. A1 actually is A. So to construct A2, remember that this is just A plus A over 2. So this exactly gives us what does the operation. It adds one element, the element of the middle, to this set. A3, this is 3 times the sum of A over 3. So here I just put 4 or 5 points, but it actually it may be more. So here we see that this set is the operation each time is adding point, not necessarily at the middle of the previous ones, but filling the gap between the function. So if we go back to our inequality, what we see is that this distance, Hausdorff's distance, is what we see the diameter of the projection of the set, the point x belonging to the convex hull. The convex hull is the segment from this and this, and each time I take point x in the segment, you see that what the operation AK put is add points in between. So each time the diameter is smaller. This means that this quantity is when k grows goes to 0. This is which explains the fact that the set, this operation AK makes the set at the infinity, makes it convex. Concerning the problem of the projection, actually in optimization and variational analysis, there is a very interesting problem called the Klis conjecture, which says the following. Actually, the result is this one. Consider that we have a closed set A in Hilbert space. Of course, all of us knows that if it is convex, then the projection mapping is single valued everywhere. The most important part of this theorem is the converse. We say that this set with only one projection is called Chebychev. The Klis theorem, proved in the 60s, the beginning of the 60s, says that every weakly closed, and it is important, every weakly closed Chebychev is convex. So this actually the conjecture, to my best of knowledge, is still open if we remove the assumption of weakly closed. So this theorem tells us that somehow the projection could also be used to measure the non-convexity. Of course, it says that if the projection is each time singleton, which means the diameter 0, the involved set is convex. So what we ask in our case is that still for general set, not necessarily convex, having some information about the diameter of the projection, also allow to have information about the shape or about how much is the set not convex. Yes. this actually we have already done this part of the problem, the question, to find some estimates like this one, and at this moment we are looking to extend this to analytic to function. I mean, to have some relation between the estimating the difference between a function and its convex, closed convex hull, using the associated resolvent of the self-differential. And also we are working on some application in to have some duality gap for non-convex optimization, and also for problem of calculus of variation. So the talk is, what we do is first recall or do some review on this Chebychev set. We will introduce what we call, perhaps it's a new name, but possibly as a concept it is not, what we call weak projection of onto closed set. We relate this weak projection with the problem of the convexity of Chebychev set. We will speak about weak Chebychev set. And in the second part, short one, we will introduce this relationship between the lack of convexity and the diameter and the shape of the associated projection. So what we call this first part, I just recall or do review of this Chebychev set. So what we call weak projection of onto the set A is I consider all the minimizing sequences yk, or that says that the distance goes to the amount of the distance to the set A from the point X, and consider all the possible weak limits of such sequences. Actually, this set is weakly closed because of its definition. Of course, in finite dimension, it coincides with the usual projection, because weak limits are strong limits. Even more, if the set A is convex, due to Mazur theorem, the set is weakly closed, and also I take here the strong limit, and so this coincides, this weak projection coincides with the usual projection. Of course, other concepts like weakly closed or approximately compact due to Vlasov, I don't remember here, I don't recall here the definition. In such usual standard assumption dealing with the Chebychev set, on all of them, this weak projection reduces to the usual one. Actually, this weak projection may be strictly larger than the usual projection. That imagine of on this set, consider the unit sphere, unit circle in L2, yes, and here, of course, outside 0 there is no problem. But if you project 0 onto this circle, you have all the circle. And of course, if you take the weak projection, this is all the possible weak limit of. Actually, we can take the all possible limit of this circle, which is exactly the whole unit ball in L2. So this could be. These are different concepts. To do this, to prove this, to deal with this, there is a classical approach now introduced in the 60s by Asplund. If we consider this Asplund function, EIA, the indicator of I plus non square, we can calculate its conjugate function, very easy. And in a result we have with Correa, Marco Lopez, and other colleagues, we proved that the self-differential of this conjugate function actually is related to this, what we call weak projection. Actually, in our approach, we use supremum function, and we developed other calculus. Actually, I believe that this result could also obtain just by doing some calculus, subdifferential calculus on this function, actually the distance function. And so what we can do is use this classical approach, but taking part of this new formula we had for the conjugate. Actually, we have proved the following result. Given a proximal subset A of H, this is a set having always unique at least one projection. It is equivalent to say that this weak projection set is convex for every X, or it is convex in a convex dense subset of X. And both of these two conditions gives me the convexity, unfortunately not of the set A. If not, the conjecture will be solved. If not, but the convexity of the weak closure of the set A. Of course, if the set A is weakly closed, this is the Klee assumption, the assumption in Klee theorem. So all these three are equivalent. Observe that in finite dimension, these two conditions are equivalent, and actually the weak projection is classical projection, and we recover the classical Bunt theorem. So this is the result we obtained, and I escape the proof. Yes, and unfortunately we cannot get more than the convexity of the weak closure. This is example here, the same. Take the ball in the unit ball in L2 except 0. So the projection is always convex. The weak projection coincide with the usual one outside 0. At 0, it is the unit ball, so it is convex. But of course, the set A is not convex. But of course, the weak closure is. And we have this equivalence, which is a weak version of Klee theorem. So A is convex in any Hilbert space, if and only if these weak projections, the weak projection is unique everywhere. Yes. So now to go to this function to estimate no convexity. Remember that this is our function. This deviation actually
5 minutes left.
Yes, yes, of course. So this is deviation function. It is complicated to write it this way, but just observe that if I consider this delta A to be the convex whole of this function, my deviation function is just this nice function. I can manage, and I even can compare with this function, and I can compare with the Hausdorff distance. And actually, this is why this function is measurement of the no convexity. What we did is to give expression of this quantity here. Yes, and actually it is this one. What we proved is that this quantity here is given by means of this. So what we perhaps I go the simple, if I simplify this part, yes, I arrive to this. In case H is Rn, just perhaps we keep with this information that the Hausdorff distance of the set A is compared to the supremum of the diameter of all the possible projections. So this is what we call quantified version of Klee theorem. You see here that, or we see here that if we are in the condition of Klee theorem, the projection is unique everywhere, the diameter is 0, and the Hausdorff distance is 0. So the set is convex. Yes. In this last result we obtain is that to compare where the supremum is attained, actually we have relation. The supremum of this deviation function is attained at the point x0, if and only if this it is x0 itself is a convex combination of its convexified points. And I finish by just the list of references. This is the famous Asplund's paper, where all this stuff about Chebychev set or using convex analysis for Chebychev started. And these papers where we have established some result about the subdifferential of the conjugate of the supremum function. This one on the convexity of some criteria of convexity, and this one is standard. So I stop here. Up to you, Alex.
Thank you, Abderrahim. An interesting idea to measure non-convexity. I've never heard actually about such a problem. So for me, everything is absolutely new and natural. I can't resist asking a question.
Yes,
how
please.
essential is the assumption that the space is Hilbert?
Yes.
So
Actually,
theoretically, you can formulate projections in any spaces, not necessarily in
yes.
Hilbert.
Yes.
Of course,
yes.
projections might look weird, but they still exist, may
For sure.
exist.
Yes, for sure. Actually, because of our methods. Actually, what the starting point of this result was this nice formulation of this the conjugate of Asplund function. So to be in a Hilbert space, we can have the explicit formula of the conjugate of this function. This is the unique point where we use Hilbert. Of course, I suppose that this can be extended to more general context, and actually it is the problem of Chebychev set is even extended to very large family of Banach spaces, uniformly convex and all this stuff. But you are right, Alex. There are many things to do.
Okay, thank you. A very quick question from Renier.
Yes, very quick. Thank you very much, Abderrahim. Very nice talk.
Thank you very much.
These results are contained on the 3 paper that you proposed before in the bibliography, or there is another place in which we can read these results?
Yes, actually, yes. Actually, all what concerns this function of measurement can be found for instance in this survey paper. It is a nice paper. Yes, but these authors are from the community of convex geometry. So you will not find there the part of variation and analysis. Yes. Yeah. Concerning the second part of this Klis theorem, of course, there is the paper of Klis, and also many works by Hilbert, Uriti, Borwein, Van de Eberhard, and many authors using this approach of relating convexity to the differentiability of the conjugate function. Yes, okay. Actually, this even it amounts to Rockefeller in the convex case, and I hope this part concerning this relation or this estimates using the projection. This is ongoing paper. We are sending now, and I hope I can send it to you very soon.
Thank you. Thank you very much.
Okay.
Okay, good. So thank you very much, Abderrahim, for your very interesting presentation.